All right, YouTube, welcome back to another Chem Complete episode. And right now we're going to be talking about acids and bases in the context of organic chemistry. And this is going to be one of a two-part lecture because there's quite a bit of acid-base chemistry that encompasses organic chemistry. And in fact, when you start getting specific about your terminology, almost all reactions can be classified as acid-base reactions in organic chemistry because we're going to exchange electrons back and forth. And when you look at Lewis acids and Lewis bases, they deal with exchanges of electrons. So to get started, when we were originally talking about acids and bases in General Chemistry 1, we dealt with the Arrhenius definition. And the Arrhenius definition was very limited in scope. It said that any compound that would give off H plus in water, it had to be in water, would be considered an acid, and then any compound that would give off minus OH in water would be considered a base. And then we start to move a little bit beyond that, and the next realm of acid-base chemistry that's not as advanced as Lewis, but is still important, is the Bronsted-Lowry definition. And so when we deal with the Bronsted-Lowry definition, we're really going to do two things. We're going to define a base differently, and we are also going to remove the fact that these have to be occurring in water. They can occur in any type of solution. So the Bronsted-Lowry definition of an acid is a substance that will donate, now we're still going to focus on protons, so it's going to donate an H plus in solution. And that solution can be anything. It doesn't have to be water. And then when we define the base, we're not really going to focus so much on hydroxides, even though those are still considered a base under the Bronsted-Lowry theory. We're really going to look at anything that is able to accept H plus in solution. And so this will start to open up new avenues for bases, because now something like ammonia, which is very much a base, is counted as a base in the Bronsted-Lowry definition because ammonia could accept a proton to become NH4 plus, right? So if I take a look at, that's supposed to be a plus up there, if I take a look at the Bronsted-Lowry definition, I get a much larger range of what can be considered an acid and what can be considered a base, which is a good thing when I'm trying to capture basically a lot of different substances and classify them as acids or bases. So another very important concept that we want to talk about is the idea of conjugates. And most of this should be stuff that you went over in general chemistry at some point. When we deal with conjugates, we're really talking about what's going to result on the other side after an acid and a base have reacted. So for instance, if I take H2O, and we'll stick with ammonia because we're using that example, right? And I subject those two to one another, and I say what I'm going to end up getting is NH4 plus OH minus, right? So the H2O gave a proton over to the NH3, and now we have NH4 plus and minus OH. So what you want to be able to do here is basically two things. First of all, can you identify the original acid and the base? Well, in this case, the NH3 accepted a proton. So if something accepts a proton, it is a base, according to the Bronsted-Lowry definition. And that means that water in this case is going to be acidic. So that'll be our acid. Now the conjugate is going to be what results due to the exchange. So this is not a conjugate base. This base creates a conjugate acid. It's now acidic because it picked up a hydrogen, right? So it's got an extra hydrogen basically bound up to that nitrogen. And so the acid is going to end up creating a conjugate base. And while this is all still very general chemistry oriented, it's incredibly important in order to understand the way in which organic reactions may be favored for one side of a reaction versus another when you're dealing with a sort of an acid-base equilibrium. So if I were to take a look at this, these would be another set of conjugates. The acid is going to create the conjugate base here. Now, in your notes, if you're following along or if you keep up with these lectures, you want to make sure that you put a star next to this or keep this in mind. And that is that the strength of a conjugate is inversely proportional to the original acid or base. Running out of room down here. Okay. So what does that mean? Basically, if I consider H2O inversely, if I consider H2O to be an acid, and think about this, H2O is neutral. We drink it all the time. H2O is not really considered an acid, but in this case it's behaving as an acid. So I would classify H2O as a weak acid. So if that's the case, it means the conjugate should be very strong, and indeed hydroxide minus OH is considered to be a very strong base. And so this is going to be true all the time whenever we're dealing with this. So for instance, if I take HCl, right, and this becomes Cl minus is the conjugate. So this was the acid, something I'm not even showing whatever's taking the H plus in this case, but the conjugate base here would be Cl minus. So do you think Cl minus would be strong or weak? Well, hopefully you realize that this would be very weak, and that's because when we take a look at HCl, HCl is considered to be a very strong acid. So strong that we get 100% dissociation whenever we put it into solution. It's going to completely ionize into H plus and Cl minus when we put it into solution. So very, very important to understand that these guys are inversely proportional. If I use a strong acid, I'm going to get a weak conjugate base. If I use a weak base, I'm going to get a strong conjugate acid. All right, back and forth like that. So we're sort of saying strong and weak, and these are qualitative terms, right? Okay, so HCl is strong in comparison to what? Acetic acid, yes. Acetic acid, the acid in vinegar, is a weak acid compared to HCl. But then if I compare acetic acid to water, acetic acid is a strong acid compared to water, right? But it's a weak acid compared to HCl. So what I'm getting at is these terms are relative. They're qualitative in their nature. When I say strong, we need some sort of definition of strong. And so in order to take some of the qualitative element out of this and go into some quantitative or numerical assessment of acids, we use Ka. So you guys should be familiar with this if you took general chemistry 2 when you're doing equilibrium constants. Ka is the equilibrium constant for an acid when we're talking about how readily an acid will dissociate. So if I take a general acid, Ha, and I place it into water, we can represent this as H plus, right? How effectively the Ha gives off H plus, and I would have A minus left over in this case. So this is a general equilibrium of some sort of usually a weak acid when we're talking about it by general chemistry standards. So what we end up taking a look at, if you remember your equilibrium constants, it's the concentration of the products, meaning the molarity of the products, over the concentration of the reactants. And because H2O is a liquid, primarily you could view it almost as a solvent in this case, we're going to take just the concentration of HA. The liquids drop out. We only really deal with the aqueous portions that are inside the water. And so this is the equilibrium constant that we would have. Ka is represented by this here, right? So let's think about what makes something an acid. Well, we said an acid is something that can give H plus in solution. So if an acid is able to give off lots of H plus, we're going to, in a relative term, we're going to call that a strong acid, right? So if I have two acids, whichever one can basically give off hydrogen or H plus ions, protons, at a more rapid rate, that's going to be the acid that we choose, or the acid that we pick to call the strong acid compared to the other one. So coming back to this, if you look at this, if by definition a strong acid is one that produces or gives off lots of H plus, that means that in order for HA to be a strong acid, it should primarily be headed in this direction, producing a lot of H plus. And so if I have a lot of H plus, I find H plus in the numerator, meaning I'm going to, as H plus sort of blows up numerically as it gets larger and larger and larger, the top of this fraction gets larger and larger and larger, so therefore Ka gets larger and larger and larger. So that means that a large Ka is going to equal a strong acid, right? Now, in organic chemistry, and in fact many chemists tend to use the inverted scale, the logarithmic scale of pKa, and you should have seen this somewhere before with pH, right? So pH is really a representation of the H plus concentration, and so pKa is really a representation of the Ka constant. And the way that we do this is you do a negative logarithmic transformation of Ka, and that will give you your pKa. Okay? Now, because this is a negative logarithmic transformation, that means these values are going to become small the higher that these are. So a high Ka will give a small pKa. And that makes sense. Think about it for pH for a second, right? If you, most people know the pH scale, if you consider that lots and lots of high H plus concentration means that you would have a strong acid, so high H plus concentration leads to a strong acid, the inverse means that a low pH is going to be a strong acid. And that's absolutely right. If we say something has a pH of 1, we're saying that that's a strong acid compared to something that might have a pH of 5 or a pH of 7, which then becomes neutral. The larger pH becomes, the weaker the acid. Well, same thing here. The smaller the pKa, the stronger the acid, and that's important to keep in mind when you're working with this. Okay, so if you take a look at an example, so let's take a look at acetic acid, which we kind of mentioned, the acid in vinegar. This is an organic acid. You should know your organic functional groups by this point. This is a carboxylic acid. Okay, this is the proton in particular that's acidic here. And let's say that we put this into water, right? So that's just like vinegar. Vinegar, when you buy it in the store, is a mixture of acetic acid and water. So if these two were to go back and forth, what I would technically be making is H3O plus, if this were to accept a proton, plus CH3 C double bond O, O minus, right? Now, this would be the conjugate acid. I'm going to abbreviate here. This would be the conjugate base. This would be the base, and this would be the acid. So, hopefully you realize acetic acid can be somewhat strong, but it's not incredibly strong. We still use it, whether you put it on French fries or you cook with it or whatever. You wouldn't dump a bottle of hydrochloric acid into your food and then utilize that, while you're eating. So this is going to be relatively weak, and it turns out that the pKa value for acetic acid is around 4.75. And then the pKa acid for the H3O plus is approximately, this is on a relative ranking compared to HCl and everything else like that, is 0. The pKa is about 0. Okay, and you can't have a pKa of 0. You can have negative pKas or pKas that are less than 1. So if I compare these two, which one of these is a stronger acid? All right. Hopefully you realize it's the H3O plus because it's got a lower pKa value, meaning it has a higher Ka value. And so that would be the stronger acid. And another thing you really want to star or point out and remember is that when we deal with reactions, I'm going to abbreviate here RXN, you'll get used to seeing that. Reactions will favor the weaker acid, meaning that we're predominantly going to say in the form of the weaker acid versus the stronger acid. And here's why. Think about this. We said that acids are going to be groups that are effective at rapidly giving off their protons. So if I'm saying that H3O plus is a stronger acid, right, and that this is a relatively weak acid in comparison to H3O plus, that means H3O plus is able to send H pluses back over to the conjugate base to reform acetic acid at a much more rapid rate than the acetic acid can push over to the H3O plus, right? So in other words, acetic acid is kind of crappy at giving H pluses off relative to H3O plus, right? So as soon as acetic acid is able to get one of those hydrogens onto an H2O to form H3O plus is going to fire back much more in terms of its H plus generation and send it back to the acetic acid. So that means that primarily the acetic acid is what we would find, and only a very small amount of the H3O plus is going to be found in this equilibrium or in this solution. So hopefully that makes sense. It's the weaker pKa, the weaker acid, that is going to be favored in these solutions. And by the way, pKa, because we're doing logarithmic transformations, this is going to be on a 10 unit scale, right? So 10 to the x is what we're talking about. So if I have something with a pKa, and we'll set it to 0, right? And then a pKa of 1, 2, 3, 4, and then 5, which we'll talk about in a second, because this is about 4.75 if we were to round, right? The difference between a pKa of 0 to a pKa of 1 is a factor of 10. And the difference between a pKa of 0 to 2 is a factor of 100, right? Because 10 to the second is equal to 100. So then 0, I'm starting to kind of run out of space here, 0 to 3 is going to be 1,000. And so 10 to the third is equal to 1,000. I think you get where this is going, right? So if I had 4, then that's 10,000. And if I had 5, that's going to be 100,000. So what does this tell me? Well, this tells me that for every 1 H plus that the acetic acid is able to effectively send over, the H3O plus can send about, it's not exactly 5, but close, the H3O plus can send about 100,000 more H pluses, right? So think of it that way. If the H3O plus is sending over 100,000 protons for every 1 proton that the acetic acid sends over, well, that's pretty pitiful on the acetic acid's part. So we're really talking about most of the solution being in the acetic acid form. The H3O plus is not going to sit around long enough considering this ratio or this exchange. Okay, so hopefully this made sense as an introduction to pKa's and organic chemistry, organic reactions, and how to look at pKa's to predict which side of a reaction would be favored. We're going to talk about Lewis acids and Lewis bases next time, so hopefully you guys found this lecture useful. Please remember to like, comment, and subscribe. You will get all the up-to-date information. I'm starting to do more and more practice sessions now, so you can use those to get ready for your tests, your quizzes, whatever else. And I'm looking at some point at trying to implement some sort of an online Q&A session or some sort of an online office hour for my subscribers and people that are interested in asking organic chemistry questions. So other than that, I think that takes care of it for this lesson. I'm going to wrap it up because we're getting close to 20 minutes here. So thank you guys very much. I will see you for the next lesson. Please make sure you turn in for part 2. and have a good rest of the day.